So everybody, we're going to flow into our first panel. No? Okay. Yeah, my apologies. We're going to get the stage set up here in just a second. And I also wanted to say, if you've ever wondered, how do they actually know that? How do they know what the flow rates are, how much sedimentation's in there? This next panel is going to help us understand how they know that. So the nice part is we get to hear from the folks that actually know how to measure this, how to understand the science and the data behind what it is that makes our creeks flow. So this is a really great opportunity to, I'm just going to say, get your master's degree. Maybe not your PhD today, but you're going to understand a lot more by the time this next panel is done. If the team from the U.S. Geological Survey Colorado Water Science Center, notice how I said that fluently? No? Oh man, this is rough. You're rough. I love it. Is going to present an overview of its comprehensive monitoring network in the Fountain Creek Watershed, developed with support from numerous partners in the basin. The session is going to begin with a presentation highlighting the key components of the USGS network, including stream flow and precipitation monitoring, water quality and sediment sampling, biological and ecological assessments, and geomorphic change mapping, along with insights into the stories these data reveal. Following the presentation, a panel discussion will explore current challenges and the real-world applicability of USGS science and data. So I'd like to welcome the scientists who track the data behind the drama. As we've already heard, schizophrenic is maybe the word that we were using for this, but the data behind the drama. Let's welcome our scientists up here. They're going to introduce themselves, so thank you so much. Let's welcome them up here. Thank you.
Good afternoon, everybody. My name is Matt Ely. I'm the director of the USGS Colorado Water Science Center. I've learned two things: keep one hand on my paperwork and cool it with the puns. I'm going to say a few words, and I'm going to turn it over to my colleague, Crystal Brown, to give a bulk of the presentation. I will quickly introduce us. We've got Brandon Forbes, our Associate Director for Hydrologic Data. We have Dustin Etheridge, who is our supervisor for all hydrologic monitoring in southeastern Colorado. We've got Crystal Brown, who is our Deputy Branch Chief for Hydrologic Data, and we have Dr. Carl Byrne, who is a research scientist with us. Do I have a clicker for slides? Here it is. You know I'm going to screw this up. So we're going to talk, as we were introduced, we're going to talk about the very complex and interdisciplinary science that we conduct here in Fountain Creek. And for a water science center, this really is kind of one of the best examples of using all of our capabilities as federal scientists in one watershed. We don't always get this opportunity to do this breadth and scope of scientific investigations. There we go. Quick introduction, the Colorado Water Science Center. We're in the USGS, which is in the Department of Interior. We don't regulate and we don't manage, which is a really nice place to be. We're a science agency within the Interior. We are partnered with our sister agency, the Bureau of Reclamation, under the Assistant Secretary of Water and Science. We are considered a field office. We're a place-based organization. And Colorado is a big state, and it can be difficult to get to certain spots at certain times of the year. So we've got 4 offices across the state. Carl and I are up in Lakewood on the Denver Federal Center. Brandon, Dustin, and Crystal are down in Pueblo. We also have our Western Slope offices in Grand Junction and a smaller field office in Durango. There's about 120 of us, fewer now than there were a year ago. Pause for laughter. We are hydrologists, hydrologic technicians, biologists, chemists, ecologists, soil scientists, IT professionals, administrative staff, and we do all things water. We're probably best known for our stream gauges and snow monitoring, precip gauges, but we also do a lot of interpretive studies with those data. And so now I'm going to turn it over to Crystal to talk about some of our Fountain Creek science that we've conducted.
Thank you.
Well, actually, nope. Sorry. I did have another slide that illustrate the point I just made. I apologize. Again, we do all sorts of hydrologic studies, both of the natural and the anthropogenic systems. And although the issues are very, very complex, We provide those science and those data for folks like you in the room to then make the even tougher management decisions. Everything we do is public and publicly available and for use by everybody. So all the things that we're going to be talking about today, it's all available through reports and data releases. And if you want to know more, you can certainly get in touch with any of us and we can provide those products to you. Now I'm done.
Afternoon. Thank you. My name's Crystal Brown. Like Matt said, I'm out of the Pueblo office. I'm going to give a high-level overview of what we do for the Fountain Creek monitoring. Before I get started, I wanted to highlight that QR code. If you scan it, it takes you to a geo-narrative that was developed by the USGS that summarizes all of our monitoring that we do on Fountain Creek, has a lot of interactive maps, takes you to all the real-time data throughout Fountain Creek, and then also the reason I like it the best is it's a great repository for almost all of the USGS publications that have been completed throughout Fountain Creek. So, interestingly, Fountain Creek is one of the most intensely monitored watersheds for its size in the entire United States by the USGS. All this monitoring that we do is driven by real management concerns and funded through different cooperative partners as well as the USGS. Lots of different entities did contribute to this monitoring on Fountain Creek. They see a lot of value in understanding what's going on and the trends and processes. Every single year, the USGS contributes over $400,000 to this monitoring program, and these other cooperative partners contribute over $1.6 million. These partnerships, what it's allowed us to do, have enabled us to produce a lot of really high quality science. And I'll talk about this in a couple of slides, but this is exciting. In cooperation with Colorado Springs Utilities and the City of Colorado Springs Stormwater Enterprise a few years ago in 2023, we did a program refinement where this will allow us, and I'll explain what we did into the future to be able to have an even more sophisticated understanding of what is going on within the watershed. So this is just a shout out to many of our partners in the Fountain Creek Basin that we cooperatively work with. I'm sure I forgot somebody, and if I did, I apologize, but City of Manitou Springs, the U.S. Army, Colorado Springs Utilities, Pueblo County, City of Pueblo, City of Colorado Springs Stormwater Enterprise, Southeastern Water Conservancy District, City of Fountain, the Air Force Academy, and the Air Force, and then the Pikes Peak Regional Water Authority. So one thing I did want to highlight is, before I dive into the Fountain Creek monitoring program, is that all of our USGS data is collected exactly the same throughout the entire nation. This is really powerful, this national consistency. So all the stream flow data, all the water quality data that we collect in Fountain Creek is collected the same exact way, whether it's a USGS site in California, Maine, Florida, Nebraska, it doesn't matter. But that national consistency is extremely powerful. And on top of this, we have all of our meters we send into it's called the Hydrologic Instrumentation Facility. Everything's calibration checked. And then all of our folks are trained exactly the same exact way through national training courses as well. So that national consistency is huge. And then one more thing I did want to highlight is, if you scan that QR code, it will take you to a website, USGS website called Water Data for the Nation. And it is a nice repository for you to access all of our data. All of our real-time data throughout the entire nation can be accessed through this site. If you have particular locations that you're interested in, you can create yourself favorites list through this site, so that then you can easily go check them at any time you want. And you can access what's called USGS National Water Dashboard, which is an interactive map where you can look at all of our real-time data, and then also other information such as the weather data. So this gigantic storm as it's occurring in real time. You can create what are known as user water alerts. And so if a user has a special interest in a particular location, you can go in and put your own thresholds in there. And then if that threshold is met or exceeded, you'll get either emails or text messages sent directly to you, depending on what you sign up for, telling you what the conditions are in the river. All of our historical data is there, and then also this is very powerful in that you can access all of our data through this website in a machine readable format. So now Fountain Creek, everybody in here knows that it's about 926, 927 square miles. This map shows the outline of it. Huge elevation changes from over 14,000 feet at the top of Pikes Peak to less than 5,000 feet at the confluence in the with the Arkansas River down in Pueblo. And then what's really interesting is that a very significant amount of the water that is used within the Fountain Creek watershed comes from sources outside of the watershed itself. A lot of these are trans-mountain diversion water sources. All those little arrows that you see up there, those are actual different trans-mountain diversion structures coming across the Continental Divide, bringing water from the west slope to the east slope. So now I'll explain a little bit more about this program refinement. Within the Fountain Creek watershed, the USGS monitors over 60 locations for things such as stream flow, precipitation, continuous water quality, discrete water quality. Those are the actual water quality samples. We do suspended sediment monitoring, geomorphology assessments at 10 sites, and then also biological surveys every single fall. With Colorado Springs Utilities and the City of Colorado Springs Stormwater Enterprise a few years ago, we decided to refine the program, and we created what are known as core sites. This spreadsheet right here was a document that we worked off of in order to be able to produce this program refinement. Those first couple columns are just site identifications. The next column right next to it in pink, if it's highlighted in pink, that's one of these 10 core sites. And then all the different columns after that are what we monitor for. So stream flow, continuous water temperature, your discrete water quality sampling, your biological surveys every fall, suspended sediment, and geomorphology. The goal with this was to create across a single line at all these 10 core sites, fill in as many colors as we possibly could, indicating that we sample for that. And the reason behind this, the reason we wanted to do this is we wanted to sample everything as close as possible at these core locations exactly the same so that there's no holes in space or time. And this will be very powerful in future watershed assessments. In order to be able to do that, we had to add continuous water temperature at 9 of those locations. And then also we had to refine our discrete water quality sampling program slightly to where now all of those 10 core sites have a minimum of 2 times a year. They get sampled during a cold season and a warm season, so the summer months and the winter months, as well as a third sample that occurs in October, right around the same exact time the biological assessments occur. And then also, all these 10 core sites get the same exact chemical analysis, chemical suite of constituents that we analyze for. And then there are a handful of oddball sites that couldn't be changed, such as geomorphology assessments and suspended sediment. They're a little different, but the bulk of everything was created with consistency. There's additional monitoring above and beyond this. That is for, a lot of this is tied to permits, and then also some of them are very specific questions at locations. But these core sites will become very powerful into the future. So now I'll dive into how is some of the data monitored or data collected and what do some of the results look like. So this is a precipitation location within the Waldo Canyon bird scar called Upper Williams Creek. At the very top of this instrumentation is a funnel, and it funnels all the precip into that instrument right there that's popped out, and that's called a tipping bucket range gauge. That monitors both the volume and how fast the precipitation is occurring. And then this graph right here is an example of what some of that precipitation data looks like. This is a graph from, I pulled 2023, and the reason being is there were some extremely high flow events, which I'll show in a few slides off of 2023. This site is for Fountain Creek at Security, which is located off exit 132. The y-axis is the total cumulative stream flow during the summer months over time. Pay attention to about that second week of June and that third week of June. Within a couple of hours, there was over 4 inches of rain at that particular location within a few hours, and then the third week of June, there was over 2 inches of rain at that particular location within a few hours. And in a couple slides, just keep that in the back of your mind. I'll show you what that actually looked like on stream flow downstream on the stream. But beforehand, I'll explain how stream flow is monitored. At any USGS stream gauge location around the entire nation, we install permanent instrumentation at that site that measures the height of the water. This is also known as gauge height. Next, hydrographers have to physically go out and they make what are known as calibration discharge measurements. They do this from the tiny little trickles all the way up through the massive flood events. There are several different ways to do this. The individual on the right, that's wading across, he's using what is known as a flow tracker to make a wading discharge measurement using a flow tracker system. So he takes about 25 different sections across the cross-section on the stream. He measures the depth and the width, and from there he's able to multiply them together and calculate an area. At every single depth section, he also takes what is known as a velocity measurement, which is measuring the speed of the water. He multiplies all that together, and then he comes up with a calibration discharge. When that flow tracker instrument right there, it sends sound waves out into the water itself, and the reflection of the sound waves back, it's able to measure the speed of the water. That middle picture right there is called an acoustic Doppler current profiler, or ADCP for short. It works very similar to a flow tracker. It's usually used at mid or high flows, and hydrographers suspended across a river or the bridge, and they walk it back and forth. But it sends beams and pulses down through the water column to be able to measure the depth and the width and also the velocity. Then that last picture on the left right there is Dustin himself right here making a mechanical meter measurement on the main stem of Monument Creek at Bijou during one of the flood events from a couple of years ago. And that torpedo, yellow looking thing, is actually called a Columbus weight. That holds the mechanical current meter in place throughout the water column. That mechanical current meter spins, and from there it measures and records the velocity or the speed of the water. Dustin also makes depth measurements and width measurements across to be able to figure out what the discharge is. So what did those rain events look like on Fountain Creek? This is a hydrograph for the same exact time period. The y-axis is what is known as cubic feet per second, CFS. That's how much water is flowing over time, same time period, off of exit 110. This is known as Fountain Creek at Pinion. So roughly a little more than 20 miles downstream. For that for that very first intense rain event that I showed you, a little more than 20 miles upstream, it produced more than 20,000 cubic feet per second in stream flow downstream. That second event was over 30,000 cubic feet per second downstream. For comparison's sake, on the Arkansas River at Parkdale, right before flows enter into the Royal Gorge on an extremely high, and I mean an extremely high snowmelt runoff year on the Arkansas River, you'll see peak flows between 5,000 and 6,000 cubic feet per second. So obviously this is many, many times higher than what you see on the Arkansas River from those snowmelt events. Next, the USGS does have a very intensive sediment monitoring program on Fountain Creek. So, as everybody in here knows, erosion, deposition, and sediment-related changes have been identified as key challenges within the basin, and this goes for any watershed, not just the Fountain Creek watershed, but sediment and the transportation of sediment. They can be a carrier for different things such as nutrients, so your different phosphoruses and nitrogens, insecticides, bacteria, viruses, and then heavy metals as well. Hopefully, one of the future goals with the sediment monitoring program is to be able to look at some of these different, understand some of these different relations between sediment and some of these other different things that are being monitored, such as the water quality. How we monitor sediment is a couple different ways. We collect samples using what are known as automatic samplers. This slide shows this right here. This is called an ISCO automatic sampler. It's located at all of our 7 main stem and Monument and Fountain Creek sites and locations. It's tied into the electronics of the stream gauge, so all the brains of the equipment, and it is triggered to sample during all those big flood events. So it's triggered by change to sample during the changes in the height of the water. That picture down below it shows some of our actual legitimate samples and what it looks like, what they look like from some of these flood events. Those first bottles to the left are right before the peak flows occur. They're pretty clear. And then as the peaks come, usually that's beforehand or right near the peak is the bulk of the sediment that comes down the stream. And then throughout the recession, the sediment samples get clearer. And then the other way we do it is hydrographers actually physically go out throughout the range of flows and they collect samples throughout the cross-section, and they collect these to make sure that the automatic samplers are collecting data that is representative of the entire stream. So that's how we collect the data. What does some of the sediment data actually show? Pay attention to those triangles on this map. Within the last year, the USGS published a scientific investigations report looking at what our sediment data says, what we have, and just the generalized trends of what it's telling us, all up and down Fountain Creek. And so if any one of those triangles points up, it indicates that the trends from 1998 through 2022 for the period that was looked at means the trends are indicating increasing sediment concentrations and sediment fluxes, sediment loads, or if the triangle's pointing down, decreases. Every single site throughout that Fountain Creek, Monument Creek watershed that we looked at for that time period, the triangle was pointing down, indicating decreasing sediment trends. And then the other thing to look at with those triangles is the size. I know it's hard to see in the back, but the larger the size of the triangle, the larger the decrease year over year of the sediment. I highlighted or I called out the three largest decreases. One is on Monument Creek at Bijou, which had an 8% decline in sediment year over year. Fountain Creek at Janitel, which is on the downstream side of the city, Colorado Springs proper. And it showed a 21% decrease in sediment year over year. And then off of exit 110, Fountain Creek near Pinion, about a 25% decrease in sediment flux year over year. One caveat I do want to state, though, is that this report literally just looked at the generalized trends. It was just a first look at what data do we have and what is it generally telling us. Didn't look into any of the drivers, what's going on, that sort of thing. The other caveat I wanted to point out is that suspended sediment flux is very closely tied to stream flow. And there were a handful of sites that did show decreasing trends in stream flow for that same time period. Next, I'll explain our water quality sampling program and show a little bit of the data that has been published off of it. Those two folks right there on the left are taking a water quality sample using a clean hands, dirty hands procedure, which is a USGS national procedure to make sure that all the samples collected are representative of the entire stream, and they're also sampled to where there's no contamination within the sample. That individual in the middle, he is collecting physical parameters with all of our water quality samples. We also measure things such as water temperature, turbidity, pH, dissolved oxygen, and specific conductance, which is a proxy for salinity. And then all of our samples are processed and preserved in a mobile laboratory and then sent up to the Denver Fed Center for the National Water Quality Lab, where they actually analyze the data for the different chemical constituents. So what does some of this data look like? You'll hear from Carl on this panel in a second. A couple of years ago, he published a water quality trends analysis report looking at 8 of those 10 core sites up and down Fountain Creek. That ball and stick diagram to the right there, it's color-coded. It shows the sites that he looked at from upstream to downstream order and corresponds it to those locations on the map right next to it. These graphs on the top show what some of his findings were. Each one of those colors or those lines corresponds to one of those locations. The first graph in the upper left hand is for selenium. Selenium is on the y-axis over time from believe it was, 1999 through 2022. And the next graph next to it is for total dissolved solids, which is, many folks honestly consider it to be like salinity over the same time period. Interestingly, what he found was decreases for the most part at most of the sites throughout Fountain Creek for these two parameters. The first question anybody is going to ask is why? Some of the potential reasons, one of the potential reasons may be less contact time that the water had with some of the geologic formations in the watershed. That map right there in the browns and the greens indicates some of the geologic formations that are known sources, high sources for some of these constituents such as selenium and total dissolved solids. In particular, your shales, Pierre Shale, and then the greens, the Niobrara Formation. That graph on the left or down or on the bottom on the left, it shows what is known as the drought well. That is a continuous monitoring well that the USGS operates just east of Pueblo. It was started in the early 2000s to current. It takes a groundwater level reading every hour. From when it was first started in the early 2000s to 2022, there was roughly half a foot decrease in the groundwater level. at that particular location. And then the graph next to it is a sum of all the diversions for the irrigated structures throughout throughout the Fountain Creek watershed from 1980 through 2022, with a trend line of best fit added to it. And so you can also see decreases there. So potentially less contact time with the water sources and the groundwater with these geologic formations. Next, this slide right here shows a table from Carl's report that looks at some of the data and the trends that he found for Fountain Creek at Pueblo, which is the most downstream site right before flows enter into the confluence of the Arkansas River. This site's maybe 2 or 3 miles upstream of the actual confluence. And it looks for this is looking at some of your different nutrients, your phosphoruses, nitrogens, and then total dissolved solids, salinity, selenium, arsenic, iron, and manganese. And what it found was for the majority of these constituents, they also did show downward trends kind of at this catch-all site right before flows enter into the Arkansas River. One thing I'm going to highlight right here, I'm going to talk about E. coli briefly for a couple of slides, and the reason being in the Fountain Creek watershed, within the next handful of years, there is expected to be an E. coli TMDL to be released fairly soon. E. coli is one of a lot of different bacteria that live in the intestinal tracts of warm-blooded animals, and these different types of bacteria have the potential to cause a lot of different diseases. E. coli in particular is considered to be an indicator bacteria, to where the EPA has standards set in place where it can be sampled within the water itself, quantified, and then the EPA has standards set for the different type of waterway. For a recreational use waterway, the current EPA standard is 126 colonies per 100 milliliters. The USGS samples and monitors for E. coli throughout the entire Fountain Creek watershed using what is known as CoAlert. The end product for CoAlert is shown right here in these trays. The sample is put into these trays. They're sealed shut. All the wells are filled up. They're incubated at a certain temperature overnight for 24 hours, and then they're red. If a cell turns yellow, that indicates presence of total coliforms in that cell. If a cell fluoresces under UV light, that indicates the presence of E. coli within that particular cell. Based on the number of small and large cells that are positive, then the actual amount of total coliforms and E. coli within that water sample is able to be quantified and known. This slide right here shows some of our data. E. coli data up and down Fountain Creek from 2007 through 2015. It shows what are known as box plots. Box plots are really just an easy way to summarize water quality data at a specific location. The red box plots are for samples that E. coli samples are collected during the winter. The green box plots for E. coli samples collected during summer, and then the blue are for storm flow E. coli samples. And then I added a red line right around the EPA standard. And then this graph also separates things into the Upper Fountain Creek watershed, a Monument Creek watershed, and then it calls the Lower Creek watershed from about the middle of Colorado Springs to the Security Widefield area. And you can see the E. coli data from for this particular time period at most of these sites was above the 126 standard. Next, I'm going to touch on the biology monitoring that we do. Every single fall around September, October, we do biological surveys and assessments for fish, which we do in partnership with Colorado Parks and Wildlife. Then we also sample for macroinvertebrates, so those are the actual bugs that live in the stream itself, and then we do habitat assessments. This program began in the 1980s. And it has been had a core monitoring since 2003. And having such a long-term consistent data set has really allowed us to produce a lot of publications and understand the potential effects of streamflow management on some of the plain stream ecology. That picture right there is from one of our surveys. That is a special species of concern for fish in the Fountain Creek watershed. It is called a flathead chub. Within this biology program, currently we have 14 active sites, and 12 of these sites are considered core biological sites. And the reason they're core biological sites is because after that program refinement, now we have consistent stream flow with corresponding with that site, continuous water temperature data, and now consistent suite of water quality parameters that are monitored. That picture to the left of those snails, that is called a New Zealand mud snail. They're teeny tiny. They're about the size of a pencil head. They have been found and identified at up to 6 sites in the Fountain Creek watershed that we monitor, and they become fairly prolific at the Jimmy Camp site that we sample as well. They are an invasive species. And then the picture right next to it, that's one of my favorites. That's actually a dragonfly larvae from one of our samples. In 2024, with the USGS published a report that looked at all of the scientific literature, so all the different USGS reports that have been done over the last 30 years of research on the ecology within the stream. And then we also analyzed the most recent data, and some of the findings that it did find were that there have been changes at some of the sites for the ecology. In particular, there have been a loss of taxa at some of these locations, and when I say loss of taxa, some of the species that were being seen historically in the more recent years haven't been being seen, and I mean both bugs and fish. And then also the species that are currently being seen do have a greater tolerance for increased temperature, so they like warmer temperatures. All right, this report also did find that there is a persistent link between the biological communities and stream flow. And because some of the data, the water quality data was spotty, which is now rectified with that program refinement, it has identified a weaker link between some of the biological communities and some of the water quality parameters. And then the very last thing I'm going to touch on is our geomorphology program. We monitor 10 sites up and down the Fountain Creek watershed for stream channel changes. And so every single winter, we go out and we collect elevation data. The two of the ways that we do this are shown through this slide right here. That top picture uses what is known as a GPS RTK system, where somebody goes out and physically measures elevation points across the wetted part of the stream. And then the majority of the floodplains for these geomorphology sites, the elevation data is collected on the floodplain using drones, as shown in that bottom picture right there. That middle map area, that shows the actual raw elevation data from some of these surveys at one of the middle sites, location site, known as Site 5. And then once we gather all that once we gather all that data and we process it, we're able to produce these elevation maps. And what I really like are these guys right here, the elevation change maps. These elevation change maps are able to show when these studies reaches the changes over time at what's occurring. And so in this particular example, it was looking at the same Site 5 changes between 2020 and 2015. And the red shows the fill, so where the stream flow is filling in, and the blues are the scour areas. And you see changes up to about 7-8 feet in that particular location. And now I'm going to hand it over to our panel. But once again, I wanted to highlight that is that QR code, if you're interested, to take you to the geo-narrative of all the different USGS publications.
Thank you, Crystal. That was an amazing job summarizing decades of science in 30 minutes. Take a breath. All right. I've jotted down a few questions for our panelists here today. I'll try to spread the pain around a little bit. We've heard the creek referred to as, I wrote it down, erratic, schizophrenic, and maybe like the early days of the district, unruly. It seems like average water years are a thing of the past, and we're dealing year after year with hydrologic extremes, droughts and floods. So let's talk first a little bit about floods, and I'll direct this question to Dustin because he and his folks are usually the ones out there hanging over the bridge trying to chase these things. How do you measure these floods, these really flashy, quick floods? How does the river change as a result of these? How does wildfire impact floods? And then what's really important, how do we make sure that those data keep transmitting and are reliable?
Yeah, that's a loaded question there. There's a lot to unpack. So generally speaking, in terms of measuring the floods, it goes back to some of the equipment that Crystal highlighted there. Fountain Creek tends to be obviously a high sediment transporting stream, and that creates the need for the photo that Crystal showed just from down the road over here off of Bijou, utilizing that mechanical meter measurement. So the ADCPs that she mentioned, unfortunately, are only great in water that is a little clearer. So that creates a need for us to use those mechanical meters. So that comes down to then at that point timing, and the amount of data that we have on Fountain Creek, the amount of stream gauges definitely helps with that. And we've heard several of the speakers mention the frequency of floods on Fountain Creek, and you know, that's something that's going to continue to happen. It is an extremely flashy stream, and you know, something to the extent of 1921, 1965, you know, what that looks like, unfortunately, who knows? That's something that would take some potential more work with flood inundation mapping or some modeling. But, you know, flooding is bound to happen again, unfortunately. We saw that most recently in 2023, some of the stuff that Crystal highlighted. That, you know, I've been here for about 14 years, and that was the highest flow that we've seen along Fountain Creek in that amount of time. But that flashy nature is just what it's going to do. And I was joking with some people at the office. We like to say that Mother Nature is going to Mother Nature, and at the end of the day, we're at the mercy of what it's going to do and those precipitation events, how it handles that. Wildfires obviously play a big risk in that. They have a big impact. We saw that with Waldo Canyon and the tragedies that unfortunately come from that. But, you know, wildfires do create soil instability and an inability for absorbing that moisture, creates more runoff. The debris flows that come along with that pose a whole different risk. So yes, wildfires do have a big impact on that, the general flashy nature of the stream. And then from our standpoint, ensuring that our data is available to everybody in this room, to the general public, is something that we do focus on with our installations, making sure that our gauges are hardy enough to withstand that, and they're installed in a way that isn't going to be hopefully blown out. Obviously, we can only predict what we can predict, but not going to get blown out by one of these flood events. And we utilize non-contact sensors where we can to help prevent some of that, installing our main structures themselves at elevations high enough that they won't be blown out during a storm event. And Crystal highlighted the water data for the nation and water alert options for folks, and I think that those are important for people to be aware of, just from general informative standpoints, but also with emergency preparedness as well.
Thank you, Dustin. The other end of that hydrologic extreme is drought, and although we maybe have a minor reprieve today, I think that we've all seen the reports on snowpack. Brandon, can you explain, you know, how these snowpack-driven basins work, and maybe what we're up against both in this watershed and really across the West?
Yeah, absolutely. Thank you, Matt. Obviously, we know the snowpack is the most important hydrologic input into our system, and we all know that all our cities here in Colorado depend on that resource for drinking water supplies. Our economic development relies on it in all of our cities. Obviously, our irrigators, it's a critical component to agriculture in our state. Another thing we always mention is recreation. The reason we love to be Coloradans is our ability to angle and boat and raft and fish and recreate around water, and snowpack is the key to all of this. What you're hearing on the news is absolutely real. You can look at our USGS snow monitoring stations online and couple that with the NRCS SnowTel stations. We're seeing some of the lowest snowpack we've ever recorded. And this morning when I logged onto my laptop and checked on our stream gauges around the state, just to look at the health of the network and make sure there's not an issue that needed to be addressed, I like to plot up how this day's flow condition compares to the last 100 years on this day, to just see if there's an obvious outlier that shows our network maybe needs some attention. Well, it didn't need attention this morning, but what we're seeing at some of these gauges that have been around for over 100 years, we're seeing some of the lowest flows for January 23rd that we've ever observed. So what do we do from here? Well, from a USGS standpoint, our staff they just get energized by extremes, whether it's the floods that Dustin just talked about or trying to figure out how to measure these unprecedented low flows. And what that truly means is really hard work right now. There's folks out today drilling holes through ice, moving sensors where water's receding to make sure that we're providing the most accurate data to y'all so that you can make the most informed decisions today. And we really have the motto that what drives us and when we succeed is when you can fearlessly and confidently use USGS data in your decision making. And today's data that we're collecting will be used generations to come and publicly available forever and collected in a defensible way so that when our grandchildren have to make these decisions, they're basing it off what's happening today with our folks in the field. Something to be really proud of, and we'll keep delivering that data no matter what conditions arise.
Some of our staff had a snowmobile training. They have to go through periodic snowmobile training. They were out at Winter Park yesterday, and I asked the instructor how it went. He said, well, it took us a while to find some snow, but we finally did. This is late January in Winter Park. It's bad out there. Out west, when we talk about water availability, most people think flow, discharge, number of molecules, but water availability is really also constrained by water quality and sedimentation, and y'all have a flashy system here that can really move some dirt. Carl, can you elaborate on those changes in sediment and what you found in your own in your studies?
Yeah, sediment is it's a water quality concern because of, as Crystal mentioned, it can carry other constituents like pesticides and heavy metals, nutrients, things like that. It's also a big concern for moving sediment through the system. A source area generates sediment deposition, creates problems downstream, and so it's important to know how and where sediment is moving within Fountain Creek. We know we've got erodible soils in Fountain Creek, and then we know we've got a sand channel for the creek itself, and so all of those make Fountain Creek a system where there's a lot of potential for sediment movement. We've been collecting high-quality data for a number of years at a number of sites, and just this past year, as it was mentioned, we did a broad study of what the trends are in the sediment movement through Fountain Creek and saw some big decreases at certain locations, smaller decreases in other locations, and it was really interesting to me that we didn't see something consistent down the length of the stream, and that speaks to the complexity of how sediment gets moved and how the system is responding to a lot of the work that's been done in the last years to stabilize banks, stabilize soils, control stormwater, and so I think it would be really interesting in the future to try to look in more detail at how sediment is being mobilized. Flash floods, we always think of those as like, oh, okay, a flash flood, that's going to move a lot of sediment. But in Fountain Creek, sometimes it's the sustained high flows that can be big drivers of sediment movement because that's just a lot of water flowing down the channel, and that's what can really chew through the banks where they're unprotected, or not so much where they've been stabilized. So we've learned sort of a good news story that there's less sediment moving through the system as a whole. Substantial decreases in certain places, but there's a little bit more to be teased out from the sediment story. It'll probably be hard to ever tie cause and effect of particular projects to improvements in water quality, but it's something that we could look into in more detail in the future and kind of see evidence for how all the hard work and the money being spent in the watershed is actually making water quality improvements.
All right, thanks. We've probably all seen the bumper sticker, "We all live downstream," right? So we're here for Fountain Creek, but Fountain Creek certainly has an impact on the Arkansas River, and just like Pueblo blames Colorado Springs, Kansas blames Colorado, right? So from Dustin, maybe a surface water standpoint, Carl, a sediment and water quality standpoint, how does the information we're learning and collecting in Fountain Creek play into and then impact the ARC?
Yeah, I would say just from a general standpoint, more than just the general informative side of things for folks in this room, there's a lot of benefit to the data that we collect on Fountain Creek for a lot of water users. And we see that, for example, with Fountain Creek and a transit loss model that the State Division of Water Resources operates every day. The USGS helped develop that. The state runs that now every single day, and it is an extremely complex model. There's 250 lines of input into that model that come out every day that help track native and trans-mountain waters and essentially every single drop of water flowing through Fountain Creek to make sure things are accounted for properly to help them with water allocation decisions. So that impact on water users moving downstream from base flow levels all the way through floods. I mean, from a flood standpoint, in 2023, the amount of phone calls I had with the Bureau of Reclamation and their operations at Pueblo Dam and making sure that they were prepared for flood operations on their standpoint and where their handoff is to the Corps of Engineers, but also to help prevent downstream flooding past the confluence of Fountain Creek and the Arkansas. I think that that's important to note is there is a foresight looking downstream to how do we minimize impacts to the communities downstream as well. So I think that that data, the benefit that it has all the way from base flow through flooding conditions, that can't be understated. I think there's a lot of very important data there for the communities as a whole.
Yeah, and with regards to water quality coming from Fountain Creek to the Arkansas River, sediment, as we've talked about already, that's a concern downstream because of the extensive agriculture that we have along the Arkansas River. Suspended sediment, when the water slows down, becomes non-suspended sediment, and that can clog the canals and the other infrastructure that support the agriculture downstream. The really good news story that came out of the trends report that we did a couple of years ago were the decreases in selenium and dissolved solids coming out of Fountain Creek to the Arkansas River. As you go downstream, the Arkansas becomes a very salty river, and that depresses agricultural productivity. If there's more salt in the water, the crops have a harder time taking up that water, and so it's a serious impact to our farmers here in Colorado. It's also a big impact to the farmers further downstream in Kansas, and they look upstream to Colorado and ask about why is there so much salt in the water? Why is there so much selenium in the water? A lot of that does come from the section of river that flows through eastern Colorado, but a substantial amount of water comes out of Fountain Creek, and what we've learned is that Fountain Creek is contributing less to the load of those two constituents downstream. So another good news story coming out of the data that we collect.
All right, thanks. One more for me, and I'll direct this one towards Brandon. Jan Martin talked about the importance of collaboration, and this study is funded by our partners. Can you talk a little bit about the importance of partnerships and collaborations to do a multidisciplinary study like this, and how a study like this ensures that actual data and information and facts are driving the decision-making being done by the folks in this room?
Yeah, thanks, Matt. The partnerships and collaboration within this room are really what drives this incredible monitoring network that we have in place, and it's really something special. I've gotten to work in other parts of the country for the USGS, and I don't know that anything exists like this on the planet, and I'm honest when I say that. The partners that Crystal mentioned in the beginning of her program, they're critical to bring dollars to the table, monitoring dollars to support this incredible network. We certainly bring as many congressionally appropriated dollars as we can to the table, but they're limited. And it's partners like the folks in this room that really drive this incredible network. And, you know, this holistic approach from interests from all different cooperators in the basin that all have issues that they're trying to learn about and potentially solve has created a holistic network that supports everything from the stream flow to water quality to groundwater monitoring to sediment to geomorphological changes to snowpack monitoring, et cetera. And I truly believe that these tough challenges that we're facing and tough decisions that we're facing with our watershed and water management, you need all of those pieces to be able to confidently make the decisions that we're going to have to make in the future. And the reason we'll have that baseline data set is because of the partnerships in this room.
I don't know, do we have a couple minutes for questions from the crowd? I don't know if somebody wants to run around do the Phil Donahue to date myself.
Questions, yeah.
I have a quick question for Dustin. Dustin, you talked about the future of the flows in Fountain Creek, and my question is, in our project, the COS Creek Plan, is we plan to sort of restore the river creek back to its natural state, and right now it's very channelized. That will impact the flow. So when we talk about the future, the work that's done could have a big impact on that down the road, correct?
Yeah, definitely. And I think that, projects like that do have an impact, it creates unique situations for us as well to be able to ensure that we're still able to accurately monitor and provide accurate data for the public and for all the cooperators that we have. So yeah, any of those types of projects do have an impact. And, from our standpoint, just generally speaking, it's also nice to know about these projects and have insight into some of the stuff that's going on, because it helps answer questions before we have questions in a lot of ways, for us to be aware of that and potential impacts to the data we are providing down the road. But yes, that does have an impact down the road for sure. Thank you.
Other questions? Yes.
Yeah, I'm just wondering if there's been any studies on biological oxygen demand or the dissolved oxygen which is there. I mean, if we're planning on having lots of angling and that, it'd be nice to know how much oxygen is actually staying dissolved in water. I mean, those E. coli results are really high, and so I'm thinking there's not going to be enough. And also, is there any studies on microplastics and that coming out of Colorado Springs?
I know that we monitor dissolved oxygen at some of our sites. Crystal might know, some of the stream gauge sites have dissolved oxygen monitoring. One of them?
Yeah, we have one.
Okay.
I can hop in there. There's just one right now, real-time monitor at our Fountain site that monitors for dissolved oxygen in the real time, and that's more or less right across the interstate from where PPIR is.
We have time for one more question.
Yeah. Yeah, as far as I know, there are no studies of microplastics being done in Fountain Creek. That's one of those things that wherever you look for them, you find them, but the magnitude of the load is sort of an open question. So another area for research.
Maybe citizen science.
Yeah.
I am Jason Gross with Tribune Metropolitan District. We provide water to forest lakes and a good portion of the town of Monument, among other things. So we spent the last 7 years, we're very proud of getting water rights across Arkansas and including Fountain Creek, and with a terrific partnership with Pueblo and Colorado Springs Utilities, so that our residents that we serve get renewable and reusable water that we think will last far into the future. So we're very proud of that. So we're now at a point where we're looking forward, and Fountain Creek is an important part of our flows and the returns and this infrastructure, that we work with the community on. I'm too ignorant to know what are the questions I should be asking looking to the future about the health of this system. So my question to you is, what are the questions I need to be asking as someone who's developed this terrific partnership and this opportunity for, as has been said, for our grandchildren? What help me think about the things I need to be thinking about? I know that's hard, but can you help me with that?
Yeah, I have an idea for you. I was thinking about this morning, actually. I was driving over. I think one thing that we have to understand is how groundwater interacts with our surface water. Sorry for the feedback, everybody. And I'm sitting next to one of the most advanced scientists that can describe that, what happens physically in that process. But we have shallow groundwater that's discharging into our streams, and then we have reaches where there isn't any shallow groundwater, and our surface water could actually be lost to groundwater. Understanding how those two sources of water interact in our rivers is really important. And then in periods of sustained drought where maybe our groundwater levels recede, we could see more losses in surface flow to the surface, if that makes sense. And that is one area that we've yet to really dive into and understand. And Carl, I'll let you jump in. I know you're a master at this.
Yeah, I think Brandon did a... talking about me. No. Yeah, Brandon did a really nice job describing sort of this connection that we're learning about between groundwater and surface water. I was part of a study published earlier this year where we looked at watersheds across the western United States and learned that even during peak runoff, when the streams are as full as they're going to be, the snow is melting on the mountains, you're like, oh gosh, that must be running off over the surface, and that's why the rivers are so full, that's why the creeks are so high. We were able to use a technique to figure out the average age or the amount of transit time between precipitation and stream flow for those waters, and the average age was about 5.5 years. So that water that you're rafting on, that you're angling in, like that's like tearing apart your stream banks, yes, the snow melted, but it's not that same snow melt that's always showing up in the water. That snow melts, it percolates into the subsurface, and it pushes out older water. And so understanding how much of that older water is there and how it's changing is really going to help us understand the trajectory of stream flow in the western United States, because our stream flow is groundwater. Like the two are intricately connected, and the days of sort of thinking about groundwater and surface water as separate resources are kind of fading into the past as we learn about these connections. So that's what I would be thinking about.
Yeah, and I would just add to that that's something that we've discussed within our office in particular, that is probably a hole right now with the data that we collect in this immediate area is the groundwater data collection, in terms of not having a whole ton of groundwater, just general levels, or whether it's some water quality type work, but that is probably a hole in the immediate vicinity around Fountain Creek. But I think that all of this plays together to kind of go back to your question. I think that there's been a lot of steps already made toward asking some of the questions that you don't know what to ask yet. And I think that that's something that we've discussed as well, like Brandon highlighted, the uniqueness of this system and the amount of data collection there is from a USGS perspective is incredible. And I think that that's kudos to a lot of the folks in this room, a lot of the other cooperators and stuff that we work with, that there is a massive interest in Fountain Creek and in this watershed. And so I think that that's, hats off to everybody here. And I think that a lot of those steps in that direction are already there. It's just kind of like Jeff was saying, it's how do we continue some momentum now? I think more so than just with the district, but as a whole, as a community, how do we make those steps continue to go forward? How do we continue to build on that data collection, and how do we continue to gather more information that helps everybody?
Well, let's give a round of applause to our panel here. Thank you so much.